computer. Okay, 9.35, 6-cylinder, 4-stroke spark ignition engine, operates on the ideal Otto cycle and takes air in at 95 kilopascals and 40 Celsius. It is limited to a maximum cycle temperature of 1300 Celsius. So we need to know what's the maximum temperature of the cycle so that we can relate back to these 1300. Each cycle has a bore of 8.9 centimeters and each piston has a stroke of 9.5 centimeters. The minimum enclosed volume is 9.8% of the maximum volume. How much power will this engine produce operating at 2500 revolutions per minute or rotations per minute? Use constant specific heat at room temperature. All right, so when this sentence shows up, this is actually quite important because it's going to define how you guys are going to approach these problems to solve it. If you guys recall, the specific heat, CP and CV, they vary with temperature, okay? So throughout this cycle, the CPs and CVs will be varying. But if the problem states that we can use the constant specific heat at room temperature, it means we can approximate our results, makes our math easier, and you'll see the difference on the next problem, which we can't, right? So the first problem, we didn't have that option, we couldn't do this approximation. On this one, we can. Okay, so let's jump into it. So I'm doing week 8, problem 9.35. This is being recorded. And we need to know the Otto cycle before we can even start to think about anything else, right? So the Otto cycle, okay, so the Otto cycle is the one in which we're going to have, as I said, 2 isentropic transformations and 2 isovolumetric ones. Okay, so you go 1, 2, 3, 4. From 1 to 2, compression, right? You can see the volume decreases. Isentropic compression. From 2 to 3, heat addition, Q going in. From 3 to 4, the expansion, that's where we get the work output, work of the turbine, or the work output of the expansion. And in this case here, we have the heat rejection going from 4 to 1, okay? There's no turbine, it's just the amount of work that I need to be able to compress this fluid outside, and then the amount of work the piston is going to release as it explodes in the combustion chamber. Okay, so from this graph here, okay, I know that the intake of air is here because that's where air enters so that I can compress it and afterwards explode it over here. So when they say the intake of air is 95, what is it? Yeah, 95 kilopascals, and they say the temperature of the intake is 40 Celsius, which is 313 Kelvin. I know these guys are in this state here, state 1. Okay, but note that there's nothing saying that. You have to know the cycle to be able to relate these information. The other thing is that the maximum temperature is given as 1300 Celsius. Okay, and the maximum temperature, you can look at this, the maximum point of energy in this cycle is number 3. So 3 is 1573 Kelvin. Oops, 73.
Yo, Pablo, it's getting hazy.
Okay, what else do we know? The maximum volume, this guy here, there's remember there's a ratio that you guys learned from the first problem. There's a relationship between the max volume and the minimum volume. Yeah, that's the ratio there. And on the Otto cycle, there's only 2 volumes, right? Max volume is the one from 1 and 4, which are the same, and the minimum volume is the one from 3 and 2, which are the same as well. What this guy says is that the volume 2 is 9.8% of the maximum one. So what is this saying? Well, it's saying the following. Let's draw a little piston here. Little piston here. And then when the piston compresses the gas, it goes all the way up here. Okay, so we have our engine. It's operating in this Otto cycle, and it's going to put air into this little chamber here, right? When this air explodes due to the combustion, the fuel that we put in, goes all the way down here. So this guy's going to have a different volume here. Okay? And the difference, the maximum enclosed volume, we can calculate that. But this difference here is that this one is 9.8% of this one. Okay, this is the minimum volume, this is the maximum volume. Okay, so what I'm going to do now is I'll show you a little video about the Otto cycle. And I want you guys to grab some information from the video. I want you guys to notice how many revolutions the engine does for every one of these cycles here. Right? So from when we put the air in all the way to when we put the air in again, how many cycles, revolutions it was able to go. And the other thing I want to show you guys is about the bore and the stroke for us to relate the 6-cylinder to what's being said in the problem. So okay, so every time we go around this guy here and we go from 1 and all the way back to 1, no, that's 2 revolutions for a shaft. Okay, the area of the piston, well, if my bore is the diameter of my piston, well, then that means that if I take pi, multiply by my bore, which is 8.9 times 10 to the minus 2 to have it in meters, divided by 2 and have that squared, I can grab the area of my piston. Okay, this is the area of the piston in this particular engine. And then if we relate that to the stroke, right, so if we take this area here, the area of this guy, and multiply by this distance here, how much it travels, that's going to give us the displacement volume, right, how much it's displacing every time. So I multiply the area of the piston by the stroke, and I get the displacement volume for this particular engine. Okay, now remember that the thing about CP and CV, when we can take them as constant at room temperature, that makes our lives easier. And we can actually use something called K, which is just literally 1 over the other, CP over CV. And I'll show you on the table for this first time, but you're probably going to want to get used to this. Table A2 at 300 Kelvin, or room temperature. And then we have properties for air. Okay, you can guys go ahead and write these guys down. CP, we're going to consider this guy throughout, right? That's the approximation we're doing. CV as well throughout. And then K will be 1 over the other. So this 1.005 divided by the 0.17, that's 1.4. You can do it on your own if you want to. You can grab these two, or you can just grab straight. Okay. And go ahead and grab the R constant. We're using this guy eventually as well. Okay, and then the savvy little trick is that whenever that we have an isentropic transformation, we can consider these guys as fixed. Then we can use T1 V1 K minus 1 equals T2 V2 K minus 2. This relationship always will be preserved. This comes from the ideal gas equation, and then just relating CPs and CVs. Okay, so again, this is only valid in an isentropic process as long as our CPs and CVs can be assumed constant. Right? If we can't assume that, if we need to account for the variation, we can't use this relationship. And then in all of these cycle problems, what we're going to do is we're going to have to solve all the states to be able to find whatever they're asking of us. So you guys as students, you have the option of, before doing anything, just solving all the states, defining all the states, and then just after we're coming back and just seeing what they're looking for. So what I'm going to do is I'm going to find my temperature for my state 2 and my temperature for my state 4 using the information that I have for 1 and 3, okay, using this relationship here. If my T1, my T2, sorry, I'm going to solve for T2. Well, T2 is going to be my T1 times my V1 over my V2, K to the minus 1. Oops, sorry. For some reason I put 2 here, but this is 1. Which way this 2 showed up here. 1 minus 1. There you go. All right. So we have T1, it's 313. We have the K, it's 1.4. And then V1 over V2, we don't have either V1 or V2 at the moment, but we know that there's a relationship between them, right? So I can go ahead and sub in that. So that's going to be 313. And then this is going to be V1 over 9.8% of V1. This is going to be 1.4 minus 1, which is 0.4. And from this relationship here, 0.4. Okay, and then it's only numbers here, so I can solve this, and I get that my T2 is going to be 792.5 Kelvin. Okay. What I'm going to do next is do the same exact process, but for T3 instead of T2, right? Oh, sorry, for T4 instead of T2. Okay, so I'm going to find my T4 now. and my T4. Again, same equation, right? I just write it the whole thing down so you guys know exactly what I'm talking about. T3 times V3 to the K minus 1 equals T4 times V4 to the K minus 1, and so forth, and therefore T4 equals T3 to, what are we doing here? V3 over V4, K minus 1. Okay, T3 we had from the start, that's 1500. K is the same, it doesn't change, that's the whole idea. And then V3 over V4, what's that going to be?
Same as V1 over V2.
Same as V1 over V2, almost, right? Same as the inverse of V1 over V2, right? Because the 3 is the smallest one, right? So if I sub this guy in, it's going to be, my V3 is going to be my V2, and my V4 is going to be my V1. So I'm going to have 9.8 V2 here and V1 here, 9.1 V1 here and V1 here. So that's going to be inverse. So watch out for that. Something students love to forget. Okay, so this is going to be V1, V1 times 9.8, which is the same thing as V2, and the bottom here just V1, and this 0.4 again. So my T4 with this system here is 621.3 Kelvin. Okay, now that I have the temperatures, this is when I'm doing one of these problems in which I can consider these guys to be constant. This is actually makes our life so much easier because I don't have to worry about getting enthalpy and internal energy, those sorts of things, because it's just a matter of finding the temperatures. Because what we know about Q's and W's is that they're going to obey the relationship between CP's and CV's, right? What we're looking for in this cycle is how much output, work output I get out of it. Okay, and we know that when we go from, let's think about it, when we go from state 1 back to state 1, my delta U is 0, right? It has to be 0. So if my delta U is 0, the sum of Q plus work has to be 0. Therefore, the work output of this guy has to be equal to the Q that I've put in minus the Q that I'm rejecting, right? And then, so long as I can calculate Q in and Q out, I can grab my work. And this is quite simple when the CP's and CV's are constant. Why is that? Because I know this guy's just going to be CV times the delta T, right? This constant volume process here. I'm going to grab CV, multiply by the difference from T3 to T2. I'm going to get my Q in. And multiply the difference from 4 to 1, and I get my Q out. So my work output, it's going to be CV times T3 minus T2. That's how much work, energy I put in some form of heat. And I rejected T4 minus T1. So my work output will be, what is my CV? 0.718. Okay, times T3, T2, we have all of those guys. We have this 792.5 minus T2, this is T2. Sorry. T3, which is 1573 minus T2, 292.5. And I'm going to subtract that by 0.18. That doesn't change, thankfully. And then T4 minus T1. T4, 621.3. T1, 313. So my work, how many first place? My work output of this guy here will be 339 kilojoules per kilogram every cycle, right? Every time I go around the cycle from 1 back to 1, this guy's going to output 339 kilojoules per kilogram. And we're not done yet. This is just the first part of it, because if you look at your answer, you'll see we want things in power. So we're going to have to relate some things before we can do this. Now, what am I missing here? Well, I need to account for the fact that this is only for one cycle, and we're being asked for 25 revolutions per minute. I need to account for the fact that I have 6 cylinders, and I need to account for the fact that I don't have the mass yet. So I'm going to grab this value. We're going to go to a new page. If you guys want to take a screenshot, go for it. And then we're going to grab all these things that are missing. From you want to ask anything? I'll just mute you for now, okay? Just unmute yourself if you want to ask anything in the future. All right, so new page. We had that the work output was 339 kilojoules kilogram, and this is for one cycle, right? For one cycle. Okay, so now let's find the mass. And whenever you have to find the mass in these problems, what you need to do is check the state for which you have the most information, right? In this case, it's state 1, because we have the pressure, the temperature, and we also have the maximum displacement, right? The volume that we calculated. So PV, P1, V1 equals M1 RT1, ideal gas equation. I'm going to say that M1 over Vm equals RT1 over P1. And then this guy, if you guys notice, this is specific volume right there. And I have all the information that I need, right? I know the R that we grabbed from the table right in the beginning, which is 0.287 kilojoules per kilogram Kelvin. I know the temperature of T1, 313 Kelvin. And I know the pressure, which is 95 kilopascals. Kelvin cuts Kelvin. And then we're going to have be kilojoules and kilopascals. Our kilos go away, and then the joules and pascals meters cubed, right? So my V1 over my mass, which is the same thing as my specific volume from 1, that is 0.9456 meters cubed per kilogram. If we have the volume, and we calculated that in the beginning, and we have the specific volume, we can calculate the mass, right? It's trivial. So the mass will be just my volume over my specific volume, which is, if you guys recall, the volume that we calculated before was 6.16. 6.16 times 10 to the minus 4 meters cubed. That's divided by 0.9456 meters cubed per kilogram. Okay, so my mass of air going through this guy is 6.51 times 10 to the minus 4. 6.51 times 10 to the minus 4 kilograms. That's the amount of air that I have going through this this cycle, and that's in one cylinder, right? So if we want it for 6 cylinders, and mind you, you could have done this at any point. You could have done this later if you wanted to as well. Just multiply that by 6. It's just going to be my max for 6 mass total. Mass T for mass total is just going to be 6 times the mass of one cylinder. So that's going to be 6 times, it's 3.9 times 10 to the minus 3 kilograms. And that's the mass of this engine. Total mass of air that goes through this engine. 3.9 times 10 to the minus 3 kilograms. Okay, and now what we can do, we can go back and relate this mass over here with this cycle. Okay, we can multiply by the mass, and we're going to get that the work output for one cycle is 1.325. So I get 1.325 kilojoules for every time I go around that Otto cycle there. Okay, almost done, almost done. Now we need to fill, let's put it, what is the question asking? It says, what is the power? What's the power? How much power will this engine produce operating at 2,500 RPM? So the power was going to be, if we're doing 2,500 revolutions per minute, and we know that there are how many revolutions for every cycle? For every one cycle, there are 2 revolutions from what we saw in the video in the beginning. And We know that this guy is producing 1.325 kilojoules for every cycle, for every one cycle. And if you guys notice, check out what's going to happen here. Use red. Right, my revolutions, my cycles, and my cycles. So I'll be left, if I do this math here, I'll be left with kilojoules per minute, which is no good, right? We want the answer in kilowatts, so I'm going to go ahead and transform my minutes into seconds. So I know that 1 minute has 60 seconds. So I get rid of these minutes here, and I'll be left with kilojoules per second, which is kilowatts. So the power output of this guy here will be 27.6.
Is 27.6, right?
That's right. Hopefully. Unless I did
Okay.
anything wrong. Yeah, unless I did anything wrong. Yeah, so that's going to be 2,500 divided by 2, divided by 60, and multiplied by 1.325. Okay. We don't have, let me know if you have any questions. If you don't, I'll jump straight into the next one. But please speak up if you do. It's a long week today, don't forget it.